Hi, welcome to this second presentation about the best methods to alkylate carbon nucleophiles. This presentation is about the alkylation of polar organometallics by addition to alkenes. Polar organometallics are compounds with bonds between carbon and metals of the first and second group and to related metals, where no delocalization of the partial negative charge at carbon to a more electronegative atom, such as oxygen or nitrogen, is possible. Some polar organometallics are sufficiently reactive to add to simple, non-activated olefins. Such additions will proceed more readily if the newly formed organometallic reagent is somehow stabilized, but such stabilization is not strictly required. Hydrolysis of the intermediate will yield a hydrocarbon, but other electrophiles such as carbon electrophiles or halogenating reagents may be used as well. Occasionally, the intermediate may even react with the starting alkene to yield oligomers. One industrially relevant example of such a reaction would be the anionic polymerization of butadiene or isoprene initiated by organolithium compounds or sodium for the preparation of synthetic rubber. Polar organometallics add particularly readily to olefins if the intermediate is stabilized by chelate formation. Many examples of such reactions have been reported, but the regioselectivity is not always easy to predict. In some cases, 5-membered chelates are preferred, but in other instances, 6-membered or larger rings may be favored. I'll show you some examples later. A further special case is alkylation by allylic electrophiles with allylic inversion. A third special situation is the conjugate addition of organometallics to electron-deficient olefins, such as alpha-beta unsaturated ketones or esters. Because olefins react preferentially with highly polarizable soft nucleophiles, all these reactions can be catalyzed by soft transition metals, such as copper or palladium. But in particular for conjugate additions, where a 1,2 addition to a carbonyl group may compete with the addition to the olefin, copper catalysis is a convenient way to improve the regioselectivity. The main advantages of the alkylation of polar organometallics by olefins is the ready availability of the starting materials and the high speed at which these reactions proceed. Disadvantages include the low chemoselectivity of polar organometallics and that for some olefins the regioselectivity of nucleophilic attack can be difficult to predict. Moreover, polar organometallics are highly reactive, and those containing heteroatoms may decompose violently when heated to a given temperature. Because of this high reactivity and low selectivity, numerous side reactions can occur and decrease the yield and complicate the purification of the target product. This is an example of the addition of an organolithium reagent to an unactivated terminal alkene. To cleave the organolithium aggregates and thereby enhance the reactivity of butylithium, catalytic amounts of an aprotic diamine were needed. This here is one of those instances where chelate formation determined the regioselectivity of nucleophilic attack. Despite the better sterical accessibility of the terminal methylene group, butylithium added to the lithium salt of allyl alcohol at position 2 to yield an intermediate 5-membered chelate. In this example, no catalyst was needed because secondary organolithiums are more nucleophilic than 1-butylithium and because styrenes are more electrophilic than the lithium salt of allyl alcohol. The initial regioselectivity was determined by the electron-withdrawing carbanion stabilizing effect of the phenyl group. An additional intramolecular addition of the benzylic lithiated carbon to the terminal olefin yielded, after protonolysis, a substituted phenyl cyclopentane. This remarkable example may not be directly suitable for larger-scale preparations, because of the excess of benzoquinone and the mixing of oxidants and nucleophiles, but its mechanism is interesting. Organozinc reagents are not nucleophilic enough to add to unactivated olefins, but in the presence of a palladium salt and an oxidant, this reaction can proceed anyway. It is assumed that upon reaction of the organozinc compound with palladium, a palladium hydride was formed which added reversibly to the terminal alkene. Reaction of this alkyl palladium intermediate with the organozinc reagent yielded a dialkyl palladium species, which underwent reductive elimination to yield the final product and elemental palladium. Reoxidation to palladium-2 was required to regenerate the palladium hydride. This is an example of allylic displacement by a Grignard reagent. In the presence of stoichiometric amounts of copper-2, phenylmagnesium bromide was converted into a softer organocuprate, which added mainly to the fully substituted olefinic carbon of the electrophile. Without copper, the Grignard reagent would probably add to the ester carbonyl group. Allylic displacements can also be conducted enantioselectively, for instance with the aid of an enantiomerically pure copper ligand. In this example, the chiral cuprate was generated from butyl lithium and, as in the previous example, almost complete allylic inversion occurred. Unfortunately, the two isomeric products will be difficult to separate, and for practical applications, much higher selectivities will usually be required. Interestingly, Grignard reagents may also undergo enantioselective allylic substitutions with allylic inversion without the need of any late transition metal. In this example, such a reaction was accomplished with 2% of a chiral heterocyclic carbene, without any additional catalyst. Also, catalytic amounts of iron can be an alternative to stoichiometric cuprate formation, as shown in this example. Interestingly, the addition to Terz butyl sorbate occurred with high selectivity at the less strongly activated double bond, and mainly a cis olefin was obtained as product. The strong impact of solvents and additives on these reactions can be further appreciated in this example. Here, in the absence of HMPA, a clean conjugate addition took place. In the presence of HMPA, however, almost exclusive nucleophilic displacement of bromide occurred. Thus, by the choice of solvent, the chemoselectivity of polar organometallics can be steered into the right direction, and it is therefore worthwhile to experiment a bit with additives and solvents when facing problems as the one above. So, what can go wrong? One of the many potential side reactions is deprotonation of the electrophile, in particular at allylic or benzylic positions. If metal hydrides are formed by thermal decomposition of the starting organometallic reagent, these may add to the alkene to form new organometallics, as shown here. Other side reactions, such as homocouplings, were discussed in the first video of this series. Some more examples can be found in these references. The addition of polar organometallics to unactivated alkenes has only rarely been used in synthesis, but copper-mediated conjugate additions have been very popular and many examples have been reported. My next presentation will be about the alkylation of ketone enolates, a highly versatile and valuable strategy for CC bond formation. So don't miss it.